This lecture is on simple experiments. This follows chapter 10 from the Morling text. So after hearing this lecture, you should be able to explain why experiments can support causal claims, be able to identify an experiment's independent, dependent, and control variables, be able to classify experiments as independent groups or within groups designs, and explain why researchers might conduct each type of study, be able to evaluate three potential threats to internal validity in an experiment, such as design confounds, selection effects, and order effects, and be able to explain how experimenters avoid them, and then interrogate an experimental design using the four validities. So for an overview, I'm going to give two examples of experiments, and these will be examples that are from the textbook and that I come back to in this lecture as a way to explain some of the concepts. I'll do a review of experimental variables. We'll review why experiments support causal claims. I'll then review the two main types of experimental designs that are independent groups designs as well as within groups designs, and then I'll finish the lecture by talking about how we interrogate causal claims with the four validities. So the two examples from the textbook that I want to talk about was a study on note-taking by Mueller and Oppenheimer, as well as eating pasta. And again, I'm going to just give these examples of these experiments to give you a sense of what an experiment looks like, but I'll also be referring to these experiments and these examples throughout the lecture as a way to illustrate the concepts. So here's the first one. So researchers Mueller and Oppenheimer decided to conduct an experiment that compared the effectiveness of taking notes in class. So 67 college students were recruited to come to a laboratory classroom, usually in pairs. The classroom was prepared in advance. Half of the time it contained laptops, and the other half of the time it had notebooks with pens. So they're really interested in seeing whether taking notes on a laptop or computer versus longhand is more effective. So there's these two different conditions, a laptop condition and a longhand condition. They selected 5 different TED Talks on interesting topics and then showed one of the lectures on a video screen. They told the students to take notes on the lecture using their assigned method, either the ones that had to do so on a laptop or longhand. After the lecture, students spent 30 minutes doing another activity meant to distract them from thinking about the lecture. They were then tested on what they had learned from the TED Talk. And in being tested, they were tested on 2 different types of questions, factual questions as well as conceptual questions, and the results from the experiment are displayed in this graph. So what they found was that students in both the laptop and the longhand groups scored about equally on the factual questions, which you see right here. But the longhand group scored significantly higher on the conceptual questions. So the longhand group in blue, you can see, did better on the conceptual questions. And so part of the thinking or part of the explanation was that because in taking notes longhand, you're really, instead of just typing stuff down verbatim, because people that type, when they take notes, can just type stuff down verbatim, taking notes longhand, they needed to think more critically about what was being said. They needed to be able to kind of organize and synthesize the concepts in their own mind. And so that was advantageous for answering conceptual questions when tested on it. Here's another example. So some researchers at Cornell University conducted an experiment to see if serving bowl size has an effect on portion size, that is the amount of food that we decide to eat. Participants were randomly assigned to either a large bowl or a medium bowl condition. During a kitchen laboratory-based lunch, participants served themselves from a communal serving bowl. Each participant's plate was weighed before he or she ate the pasta and then afterward to determine the amount of pasta that was consumed. So we've got the graph on the left here, And this shows that participants took more pasta from the serving bowl um, if they had a large bowl compared to a medium one. So they're taking more pasta. The graph on the right shows that the large bowl participants consumed about 140 calories more than the medium bowl participants. So the researchers concluded that the size of the serving bowl influenced how much pasta people served themselves and how much they ate. Okay, so just two examples of experiments that I'll be coming back to during this lecture. So let's review some key terminology. The first is independent variable. An independent variable is manipulated by the researcher. For example, in the note-taking study, note-taking method was the independent variable. They could either take notes via laptop or longhand. Independent variables have levels, and the levels of the IV are called conditions. So again, in the note-taking study, the levels of the conditions of the independent variable were longhand or laptop. It's up to the researcher to select the number of conditions or levels in the study. The dependent variable is the measured variable that is the outcome. So in an experiment, it is thought that the independent variable affects or causes the dependent variable. And then control variable is any variable that an experimenter holds constant. So actually the term variable is a bit of a misnomer because variable suggests change or variability, or that you can have multiple different levels or scores. But a control variable is really a constant. So in the pasta study, all the participants ate the same kind of pasta and the same. They ate the same type of pasta. So that was something that was a control variable. It was held constant. All right, so we're going to review why experiments can support causal claims, and so I will go into detail on each of these, but it's because experiments can establish covariance, they can establish temporal precedence, and they can establish internal validity by ruling out confounding variables. Again, when we talk about internal validity, we're talking about our confidence that it is the independent variable and nothing but the independent variable that causes changes in the dependent variable. So a well-designed experiment is able to rule out alternative explanations for the findings. Okay, let's start with the first one, the first criterion that experiments are able to establish covariance. Covariance is really indicated by a difference in group means. So in both the pasta study and the note-taking study, they were able to show covariance because they showed that there was a difference between the two experimental conditions. So in the pasta study, participants in the large bowl condition ate more than those in the medium bowl condition. So there's a relationship. There is covariance between the independent variable and the dependent variable. Independent variables answer the question, compared to what? And you might recall from earlier chapters that our personal experiences don't have the benefit of a comparison group or a comparison condition. So let's just say you always eat a lot of pasta at home. You can't be for sure if it's because you're used to eating out of a large serving bowl because you don't necessarily have anything to compare to. So if an independent variable doesn't vary, then there's no way to have a meaningful difference between groups or conditions, so there's no covariance. So the benefit of an experiment by having two different experimental conditions is we can see if there's a difference across those conditions, and that establishes covariance. So certainly the outcome variable is important. It could be the case that the pasta that was consumed the amount of pasta that was consumed was the same in both groups, in which case there's no covariance between serving bowl size and how much people eat. Okay, so covariance is correlation. So we need to see some relationship. So if people eat the same amount in both conditions, there's no relationship. So covariance is, of course, not just about the independent variable, it's about the relationship between the independent variable and the dependent variable. There needs to be some difference between the groups. All right. In terms of doing these comparisons, we have different types of comparison groups that experiments can set up. So a true control group is one in which a group doesn't receive any treatment at all. So not all experiments have a true control group or need a control group. So that would be one. The other way to think about it is that you can have an experiment that has two treatment groups and the two different treatments can be compared. So really the two examples that we've talked about so far have been examples that have had two different treatment groups. Okay, one in the note-taking study, the two treatments were either laptop or longhand. So two things are happening. Each group is getting a treatment. In the pasta study, there's either a large bowl or a medium bowl. There's two different treatments. So there's not purely just like a control group in which there's no treatment of any kind. And then there's a placebo group, which is a control group that is exposed to some inert treatment. So this is very common in studies of drugs or different substances. So whether it's caffeine or nicotine or alcohol, it's important to have a control group that gets, let's just say, a pill, but the pill would be inert. In other words, it would not contain the substance. Okay, so these comparisons might take place between a treatment group and a control group, between two different treatment groups, or between a treatment and a placebo group. And experiments establish covariance by looking for differences between those two groups or multiple groups on the DV. Experiments establish temporal precedence because the causal variable precedes the effect variable. The IV precedes the DV. That's pretty straightforward. In the PASTA study, the experimenters manipulated the independent variable, the size of the bowl that they used, and then measured the DV second. There was actually two DVs, how much pasta they put into their bowl, as well as how much they ate. So the dependent variable, which is the effect of the independent variable, came second. It came after the independent variable. So that's how experiments can pretty easily establish that cause and effect through temporal precedence. All right, and then our third criterion is that well-designed experiments are able to establish internal validity, and this is really of primary importance when making a causal claim, is that if you want to say that an IV causes a DV, you have to establish that it is the IV and only the IV and not anything else. So we have to rule out confounds, which are alternative explanations that threaten internal validity. Okay, so confounds are often referred to as third variables as well. So we want to rule out these confounds or third variables because confounds create alternative explanations. So, for example, in the pasta study, it would be a confound if participants received less appetizing pasta and if others received more appetizing pasta. And particularly if the participants in the large bowl condition got more appetizing pasta and participants in the medium bowl got less appetizing pasta. In that case, the finding that participants in the medium bowl condition ate less could be attributed to the size of the bowl, but it could also be attributed to the quality of the pasta, how appetizing it was. Confound. So our serving bowl would be confounded with pasta quality, and so we can't be sure which it is. Okay. So let's talk about two different types of confounds, design confounds and selection confounds. So there's a design confound when a second variable varies systematically along with the IV and therefore provides an alternative explanation for the results. So I gave you an example with the pasta study. If pasta quality was allowed to vary systematically with the serving bowl, such that those in the large bowl condition always had more appetizing pasta, and those in the medium bowl always had less appetizing pasta. We've got a second variable that varies systematically. Okay, that it's a one-to-one with our IV. And so that's a design confound. And let's just take the study on note-taking. If all of the students in the laptop group had to answer more difficult essay questions than those in the longhand group, that would also be a design confound. Because is performance then related to the method of note-taking, or is it the difficulty of the questions that they're asked? So it's important to note that there's only a threat to internal validity when there's this systematic variability with the IV. So the two examples that I've explained have been examples of systematic variability. Unsystematic variability, on the other hand, is random or haphazard, and it affects both groups. It's not the same as a confound. So the issue would be, let's just say you allow people in the pasta study, you've got two different types of pasta, and you allow people to like freely and naturally select whatever pasta they want. That is not a design confound. That's something that could produce some amount of error, and it could mess up your ability to detect differences in your results. But people naturally or spontaneously choosing what kind of pasta they want doesn't vary systematically with the IV. So it's not a confound. All right, let's talk about selection effects. A selection effect occurs in an experiment when there are participants in one level of the IV that are systematically different than the participants in the other level of the IV. This is really handled with random assignment. And it really only happens if you allow people to self-select into conditions. So let's just say, for example, that the researchers that did the note-taking study didn't randomly assign and they just allowed people to self-select into condition. Maybe it's the case that people that have better GPAs or are better students would self-select into the handwritten note-taking condition or the longhand condition, right? In that case, we've got a confound because we have people that are better students in the longhand condition systematically than in the note-taking condition. So that's an example of a confound that would be created because of a selection effect when you allow participants to self-select into condition. Again, avoided very easily with random assignment, but that's why random assignment is a core feature of a true experiment and why true experiments allow for cause and effect conclusions is because of that feature. And many kind of naturalistic research designs, people are allowed to self-select into different groups or different conditions, and it's that self-selection that muddies the water and often presents different confounds and alternative explanations. Random selection doesn't work great if you have a very small sample size. So if you just use a random procedure like flipping a coin or table of random numbers, groups can possibly get imbalanced. And so for this reason, with a very small sample size, some researchers prefer to use a matched groups design with small samples. So matching involves matching your two different groups, like your two different experimental conditions, on some important variable that could be a confound like GPA or IQ. So what you would want to do is, of your participants, have some way of measuring GPA. You'd get a ranked list, and then you take your 2 participants with the highest GPA and then randomly assign one to group 1 and the other to group 2. And then you'd move on. And you take your next 2 highest GPAs and you would randomly assign the 3rd person and the 4th person to the 2 different groups or the 2 different experimental conditions, and so on and so on. So a matched groups design is really trying to make sure that you've got roughly equivalent GPA or roughly equivalent levels of some other variable that you think could be a confound, and not just letting random chance take over, but trying to be give yourself the greatest possibility of making sure that you've got matched groups on that variable that could otherwise be a confound. All right, so let's review the 2 main types of designs, which are independent groups designs and within groups designs. So there's many different types within those main categories, but independent and within are a major distinction. So in an independent groups design, different groups of participants are placed at different levels or receive different levels of the independent variable. So for example, in the PASTA study, each participant was randomly assigned to either the large or the medium serving bowl condition. And then in the within groups design, each participant is presented with all levels of the independent variable. Okay, so it's all levels of the independent variable. So for example, you could conduct a note-taking study in which each participant took notes both in the laptop condition as well as in the longhand condition. So they would be in both experimental conditions. That's a within groups design. All right. So one type of independent groups design is called a post-test-only design. And in a post-test-only design, participants are randomly assigned to the IV and groups are tested on the DV just once. And so the note-taking study was an example of a post-test-only design. The participants were assigned to either be on the laptop or to take notes longhand, and then they were given a comprehension test. So there's random assignment, and then the DV is administered only once. That's a post-test only design. Alternatively, you can have a pre-test, post-test design. This is still an independent groups design. What you have here is you're going to randomly assign your participants to condition, and then they're tested on the dependent variable twice, once before and once after exposure to the independent variable or their particular level of the independent variable. So there was actually a study that was introduced in the chapter 1 of the Morling text, which is about the effects of mindfulness training. And so this is the example that I'm showing in the slide here. So in this study, 48 students were randomly assigned to participate in a 2-week mindfulness class or a 2-week nutrition class. 1 week before starting their respective classes, all students did the verbal reasoning section of the GRE, and then 1 week after their classes ended, all students completed another verbal GRE of approximately equivalent difficulty. So they were able to get their score on the dependent variable 2 times, and this allows the researcher to basically control for their level of GRE knowledge, and then so within participant you can see whether there's a change that can be attributed to either the mindfulness class or the nutrition class. Another way that you can handle the data is to say, hey, before the class, you can show that both groups are equal in terms of the average GRE score. So that way, if you see a higher GRE score in the mindfulness class afterwards, you say, hey, that must be due to the mindfulness class because the groups were equivalent at the start. So there can be an advantage of doing a pretest because that ensures equivalency instead of just assuming equivalency on your DV. So which design is better? Should you do a post-test only or a pre-test post-test design? Well, of course, it depends. And it depends on the researcher's particular goal. So in some situations, it's problematic to use a pretest. So if your dependent variable involves eating food, like in the PSYC condition, the PSYC experiment, or something like exercise that would make people physically tired or exerted, like if you have people eat, they can get full. Or if you have people exercise, they can get exhausted. So if you do a pretest, you run into that, and then the post-test scores are affected by the pretest. So in some cases, it's just not practical or ideal. So eating and having people do exercise, even having people do cognitive stuff, if the pretest and the post-test are not spaced that far apart, then people can get tired or fatigued by doing the pretest first. But in other situations, that pretest post-test design makes a lot of sense. So in that mindfulness study that I shared, because the GRE was separated by 3 weeks, there's unlikely to be a lot of carryover. Taking the pretest is unlikely to affect the post-test too much. And post-test designs can still be very powerful. So there's random assignment, and there's the researcher that is manipulating the IV. So it's that random assignment that is supposed to make sure that the groups are equivalent at the start. There's often the assumption that it is. Of course, it's more powerful to use a pretest because you can measure those groups and make sure that they are. But post-test designs can still be very powerful on their own. All right, so let's shift to within groups designs, and I'll talk about 2 different types of within group designs: repeated measures and concurrent measures. So here is an example of a repeated measures design, but a definition of a repeated measures design is that it's a type of within groups design in which participants are measured on the DV more than once after exposure to each level of the DV. And so the key feature here is that that makes it both a within subjects design is that participants get both levels of the independent variable. So what we're seeing here is a study that used a repeated measures design to investigate whether a shared experience would be intensify the experience of doing something. So they recruited 23 college women to a laboratory. Each participant was joined by a female confederate, which is basically just a helper of the experimenter, but the participant thinks that the confederate is a participant. So the confederate helps the experimenter, but the other participant thinks that the confederate is just another participant. So the real participant and the confederate sat side by side, facing forward. They never spoke to one another. The participant was told that, and then they were given chocolate to eat. The participant was told that the 2 chocolates were different, but in fact they were the same. After tasting each chocolate, participants rated how much they liked it. And so the results show that people liked the chocolate more when the confederate was also tasting the chocolate. Okay, so they either ate the chocolate with the confederate or alone and gave their rating in both conditions. So interestingly enough, even though it is the same piece of chocolate, this design showed that people liked the chocolate more when they ate it with somebody else. So provides some amount of evidence that having a shared experience promotes a greater liking or intensity of some experience when it's shared with other people. A concurrent measures design is one in which participants are exposed to both levels or all levels of the DV at roughly the same time, and there's only a single dependent variable. So the example on the slide is often done in infant research, in which infants are exposed to a female face as well as a male face, and then researchers are able to measure their looking preference by how long or how often or how frequently they look at one face versus the other. So this is a within subjects design, but it's a concurrent measures because the two different levels of the independent variable happen at the same time. They co-occur. They happen concurrently. So there are some advantages of within groups designs. I often will use the terminology within subjects designs. That's equivalent. So one advantage is that participants in the groups are equivalent because they're the same participants and therefore serve as their own controls. So, for example, let's go to that chocolate eating study. Some people really like chocolate, other people do not. But in a repeated measures design, people bring their same level of preference or the amount that they like the chocolate to both conditions. So their individual liking for chocolate stays the same, and the only difference between the conditions would be then attributable to whether or not they had the chocolate alone or when the confederate did, okay? If you've got a between groups design, and you've got different people that are eating the chocolate alone versus with a confederate, you will always have that potential confound. Yeah, but how do you know that in the condition in which they ate the chocolate with a confederate, how do you know that those just weren't the people that liked chocolate more anyway? Okay, and the answer is, well, but we randomly assigned, and so there's no reason to think that. Well, a within groups design completely handles that, is to say each person serves as their own control. And in both conditions, they like chocolate the same, so it can only be whether they're tasting that chocolate alone or with a confederate that would be responsible for the results, potentially. Within groups design have a second advantage, which is that they provide more statistical power. So that group differences are more likely to be detected. Recall that power is the ability of a study to show a statistically significant result when the independent variable truly has an effect on the dependent variable. Since the same people are in both groups or in all of the groups of the experiment, it reduces the unsystematic variability between groups that obscure true differences. So again, each person serves as their control. And so you're looking at, anything that could produce error or nuisance or noise or variability, extra variability into the data is really minimized when you have the same person participating in both conditions. So that chocolate study, it's not only their liking of chocolate, it's their appetite, it's how hungry they are, it's what experiences have they had during that day, it's all of those things. And all of that noise is reduced because it's the same person in both conditions. Whereas in a between groups, you've got different people in both conditions, so those people could differ from one another on a variety of factors. Even one's tendency to give high versus low ratings on a rating scale is a for example. So power is greater, really, and it's related to number one, because by serving as their own controls, error variance, unsystematic variability is reduced. And then just as like a practical advantage, within groups designs require fewer participants. So let's just say you want 20 participants in each condition. For an independent groups design, you need a total of 40 people. But if you do the same experiment using a within group design, you only need 20. So, there's times when experimenters will compensate their participants for participating. So, you can save cost, you can save time. There's some very just kind of practical reasons why within groups designs are advantageous. Of course, there are some limitations, or we'll just say some things to consider when you use a within subjects or within groups design. And specifically, there are some threats to internal validity. So one threat to internal validity is an order effect. And this is when exposure to one level of the independent variable influences reactions to the other level of the independent variable. Order effects are confounds for within groups designs because it might not be the level of the IV that cause changes in the DV, but rather the order in which the conditions were experienced. And so there's two specific types of order effects that I'll review, which are practice effects and carryover effects. So first one, practice effect. This occurs when a participant gets better at a task from practice or gets worse at a task due to fatigue. So a specific type of practice effect is called a fatigue effect, but we'll just call them both practice effects. So practice effects get better, you get better, but you can also get worse due to a fatigue effect. So if you would have people do some sort of a test or a quiz or some skill-based physical performance, people get better because of practice. And if the goal is to test people under two different conditions of an independent variable, maybe that would be like, being tested with different amounts of noise or light or temperature or instructions or whatever the independent variable of interest is, you have to consider that in looking to see if there's a change from one condition to another, your participants have practice doing whatever it is you're having them do. And so it might not be change from one level of the independent variable to the other might not have anything to do with the independent variable. It might simply be due to practice or fatigue. Another type of order effect is a carryover effect. And so this occurs when there's contamination carrying over from one condition to the next. And so this is very common in studies that look at the effects of different substances. So let's just take caffeine for an example if we want to look at the effect of caffeine. If you have participants drink caffeine and then take a test, and then you want to have them drink, let's just say coffee and then decaffeinated coffee. If they first drink coffee and take a test, and then you want to have them drink the decaffeinated coffee, the caffeine could still be in their system if you don't wait long enough before the second administration. So that would be the effect of the independent variable carrying over to the second. The effect of one level of the independent variable carrying over and being present when it's not supposed to be at the second level of the independent variable. So in order to avoid these order effects, researchers will use something called counterbalancing, which is presenting levels of the independent variable to participants in different orders. And so what we have here is we've got this repeated measures design, but we're going to randomly assign some participants to first taste the chocolate alone and then taste the chocolate with a confederate, versus have some people taste the chocolate with a confederate first and then taste the chocolate alone. And so if it's the case that, the question might be, hey, you might get an order effect to the extent that people, when they were first tasting chocolate with a confederate and then taste the chocolate alone, by virtue of having already had the chocolate, there's kind of the idea that, the first bite is the best bite, right? The first time you have something, and so the novelty kind of wears off. And so having that chocolate a second time, it just might give a lower rating because, it's less pleasurable, it's less satisfying. It's like that first bite of something is the best. So in this case, it's like if this order was first and they didn't take that into consideration, maybe it's the case that there's a higher ratings because people have that first bite when they're doing it along with the confederate, but then there's this carryover where it's, the chocolate is less pleasurable, and it's not because it's you're tasting that chocolate when you're by yourself, but it's just because it's less pleasurable because it's that, it's that second time that you've had it. So that concern would be mitigated by using this ordering, okay, because that kind of second bite effect is still there. But if you saw higher ratings still with the Confederate, that would kind of mitigate that concern. So it could still be the case that the second bite gets lower ratings, but you'd expect there to still be higher ratings with the Confederate. So that's how that concern would be addressed. There's two types of counterbalancing, full and partial. So full counterbalancing occurs when all possible condition orders are presented. With two conditions, there's only two orders. And so we saw an example in the previous slide. But the more conditions you have, the more orders you get very quickly. So with just 3 experimental conditions, there's 6 possible orders. And so it's very difficult to do full counterbalancing when you have really more than 2 experimental conditions. And so one technique is to do something called partial counterbalancing. And this occurs when only some of the possible condition orders are used. And so as a specific example, a researcher could present a randomized order for each participant, or they can do something called a Latin square, which is pictured here, in which each condition appears in each position at least once. So here we have 4 experimental conditions, experimental condition 1, 2, 3, and 4, and then we also have the order from left to right in which a person receives the experimental condition. So this particular participant receives experimental condition 1 in the first position, 2 in the second position, 3 in the third position, and 4 in the fourth position. This particular participant receives the second experimental condition in the first position, followed by the third, followed by the fourth, followed by the first. So what you'll notice is that for each, you can just assign people to each of these four different orders. And if you just track like where the condition number 1 is, you'll see that condition number 1 appears in the first position, second position, third position, fourth position. And that's also true of condition number 2. First position, second position, third position, fourth position. So all experimental conditions appear in each of the 4 slots or positions. That's a Latin square. And then how to analyze these to pick out whether there's order effects can be somewhat complicated, to tell you the truth. But the idea is when the results are all said and done, you're really hoping that, because these orders have been mixed in, you're hoping that those order effects are going to negate each other, or you're going to be able to tease them apart to see if there was a particular ordering effect. Okay, so disadvantages of within group designs. The 3 main advantages are: 1, there can be order effects, but there is a solution for these order effects, which is to use counterbalancing. A second disadvantage is that sometimes within groups designs are just not practical or possible. Let's take an example. Let's just say a researcher has designed a new way of teaching kids how to ride a bike called Method A. And the researcher wants to compare method A of riding a bike to an older method, method B. Well, it'd be very difficult to teach a group of children how to ride a bike with method A and then return to a baseline and say, okay, forget everything that I've just taught you, now we're going to go with method B. So once taught how to ride a bike, the kids are pretty much permanently changed. They know how to ride a bike now. Okay, and there's other examples, but that's just a simple one, that it's just sometimes not possible to use a within groups design. And then the third one is that experiencing all levels of the independent variable changes the way that participants act. And this is called demand characteristics, when participants pick up on cues that lead them to guess the experiment's hypothesis. So in the eating chocolate with somebody or not with somebody, if you're a participant in that experiment, you're thinking to yourself, isn't this interesting that I'm asked to taste this chocolate twice? when I'm with somebody and when I'm not. I wonder if this is what they're getting at. So that could lead to demand characteristics in which people kind of try to guess what the hypothesis is and potentially act in ways that would be in accordance with the experimental hypothesis. And so that's more common in within groups design because participants see all of the levels of the independent variable. Okay, so the next question becomes, should a pretest post-test design be considered a within groups design because participants are tested twice, once at a pretest and once at a post-test. So a pretest post-test design looks very similar to this repeated measures design, particularly when we use a repeated measures design that has the counterbalancing of conditions. It's important to remember that in a true within groups design, participants are exposed to all levels of the IV. Okay, so this is a within subjects design because participants get both IV level A and B, but in a pretest post-test design, they don't. So that's the key differentiation there. In a pretest post-test design, it's a between groups design because even though there's testing twice on the DV, they're only exposed to one level of the IV. All right, so let's review interrogating causal claims with the 4 validities, and it's the same 4 validities that we've been talking about in the class. Construct validity, which refers to how well the variables are measured and manipulated. The manipulated component is something that we're going to focus more in on because we have experiments and we have manipulated variables. External validity, to whom or what can the causal claim generalize. Statistical validity, how well do the data support the causal claim. And then internal validity, are there alternative explanations for the outcome? Let's review construct validity. To interrogate construct validity, we're really asking how well are the dependent variables measured and how well are the independent variables manipulated. In the note-taking study, you could take a look at the types of questions that the researchers asked the students, and then you could evaluate if those were actually good measures of factual learning or conceptual learning. So that would allow you to make a judgment as to the construct validity of the dependent variable. And then with the independent variable, we just want to ask how well the IV is manipulated. And I think, again, here going back to the note-taking study, it's a fairly straightforward manipulation that they either got a laptop or they had to take notes longhand. So that has pretty strong construct validity for a manipulation. I mean, that's about as clear as it gets. But in other research, when the manipulation is designed to have, let's just say, more of like a psychological effect, it's important to put something in place which is called a manipulation check. And this is a check to see, did the manipulation have its intended effect? So we can think of a manipulation check as kind of an extra dependent variable, and researchers can put a manipulation check into the experiment to convince them that their experimental manipulation worked. Again, a manipulation check not really necessary in the note-taking study because you can simply observe, hey, they're using the laptop or they're using the pen and the note paper. So it's not real important. But in something, let's take something like you want to induce a particular mood. And so we're going to have people watch a film clip or like a video clip that is designed to evoke a happy mood versus a sad mood. And then we're going to see then how that happy mood or sad mood affects their either anything, okay, test taking or interaction, the way that they would interact with another participant in a subsequent task. So what you would want to do is make sure that your video had its intended effect. So you might do a mood questionnaire after people watch the video to make sure that your your video had the intended effect on mood, and then subsequently go on and measure your dependent variable, whatever your dependent variable is. It's usually done to test the effectiveness of the manipulation to do a pilot study. So a pilot study is a simple study using a separate group of participants that's completed either before, often it's completed before conducting the study of primary interest. And this is really just used to confirm the effectiveness of the manipulation. So you could do a pilot study in which the only thing that participants were asked to do was to watch the video and then report their mood. And then using that pilot study, you can say, hey, we've got evidence that this particular video makes people happy, this particular video makes people sad, and then you can go to your primary study, just have people watch the video, and then go and do whatever the main DV of interest would be, whether it's taking a test, looking for like social interaction with a different participant or something like that. And that way your manipulation check kind of doesn't get in the way or like give away your hypothesis and cause a demand effect. So a couple different things that you can do there, but manipulation check and pilot study. All right, moving on to external validity. This is really about to whom or what can the causal claim generalize. So generalizing to other people, here are the questions we want to ask. How were the participants selected for the experiment? We've talked about sampling in a previous lecture, particularly the idea of using probability techniques like random sampling. In the research that we've talked about, for instance, the note-taking study, the 67 students in the note-taking study were just a convenience sample. And they were not a random sample. So this was just a convenience sample of undergraduates from Princeton University. And so because they're a convenience sample, you can't be sure if the results would generalize to all Princeton students or even to all students in general. You can't necessarily assume that the results would apply to middle school or high school students because these are college students. So that's one. We have to say, who are the participants, and do we think that how are they sampled, and if it's a convenience sample, will the results generalize to other people? It doesn't necessarily mean that they won't, but we have to at least ask that question. The other question would be, to what extent do these results generalize to other situations? So in that note-taking study, the note-taking study used 5 videotaped TED Talks. And so, hey, does this work for taking notes on other things? And ideally what you would want to show is that, hey, the laptop versus the longhand method, it's just not about TED Talks, it's for other lectures or it's for other content. It's not just for one particular type of content like psychology lectures, but it can be, chemistry or mathematics or whatever, or history or whatever it is. So to the extent that you can replicate the results to other situations, that increases the external validity across situations. And then, of course, they were watching videos, so would it work in face-to-face or a live lecture? These are questions related to the situation. What if it's the case that external validity is poor? So there's a convenience sample, it's maybe an artificial laboratory situation. There's this trade-off. And so in order to achieve internal validity, researchers sometimes conduct their studies in these rather artificial laboratory environments that don't really represent the real world. And so it's often looked at as a sacrifice, that many experiments sacrifice real-world representativeness in exchange for internal validity. All right, statistical validity. How well do the data support the causal claim? When interrogating statistical validity, there's the 2 main questions. 1, is there a difference that is statistically significant, and how large is the effect? And that goes with correlation as well, is do we have a statistically significant correlation? How large is the effect? Typically the larger the effect, the stronger the causal effect. In experiments, researchers use a standardized measure of effect size called Cohen's d, named after the person that came up with the statistic. And the idea here is that if there's a small d, that means a weak effect. So there's not a big difference between the groups, and we often think of that as an overlap between the groups. If there's a larger effect, there's a bigger difference between the groups, and there's less of an overlap between them. And so you can see the two different, on the graph in this upper right, you can see a D of 0.24, which is a smaller weak effect, and then you can see a D of 0.56, which is a medium or moderate effect. The same number of participants, 9 and 11, 9 and 11, but with a D of 0.24, what's being shown here is actually a mean difference that is the same, but more variability in this group. So one thing that can cause a small d is variability within condition. Okay, so less variability, all else equal, less variability within condition means less overlap, means bigger d. The other thing is that all else equal, if the variability is the same, a bigger mean difference will produce less overlap, so bigger d. So ultimately what we're getting here with a d is a difference between groups, meaning like those groups don't look the same. They're kind of non-overlapping. All right, and then internal validity. Internal validity is really the top priority when interrogating a causal claim. So there's three fundamental questions to ask. The first, are there any design confounds? So did the experiment ensure that there were no design confounds, or is it the case that there's some other variable that accidentally would co-vary along with the IV? Again, in most cases, there should not be a design confound. You'd have to really mess up. So messing up by saying like giving the better tasting pasta in the large bowl condition, that'd be a significant design confound. Making sure that people are in the note taking that they're watching the same videos in the two different conditions. So basically that researchers aren't being sloppy and introducing confounds that would vary systematically with their independent variable of interest. Okay, second question. If the experimenters used an independent group's design, did they control for selection effects using random assignment or matching? Again, you don't just let people pick conditions, and it is the most basic thing that you can do as an experimenter to use random assignment. And then third, if experimenters use a within groups design, did they control for order effects by counterbalancing? And again, this is only relevant in a within groups design. So like in the note-taking study or in the pasta eating study, the counterbalancing isn't relevant. So these are three things when you're reading published research to be on the lookout as a way to interrogate internal validity and to be on the lookout for whether there's any alternative explanations.